Okay, so part 2 of 10.7 is to look at the unit tangent vector, this capital T of t, and its formula. So the idea is we want to create a vector that's tangent to a three-dimensional curve, r of t, and the way to do that is very similar to how you create a unit vector given a specific vector. So you'll take the derivative of r of t to get r prime of t as a vector, then find the magnitude of that vector derivative, or the derivative vector r prime of t, and you divide the vector by its magnitude, and this will result in a vector of unit length, and this is known as the unit tangent vector. It's unit because we've done this operation to make it, to give it magnitude 1, and it is the tangent vector because it came from r prime of t, which will give us the tangent line to this curve in 3 dimensions. This will be a useful object throughout the rest of the course. So to look at an example, we're asked to find the unit tangent vector t of t for a given curve, sine squared of t, cosine squared of t, tangent squared of t, reading that in vector form versus ijk form. And we're asked to calculate this at the point t equals pi over 4. That might actually simplify work a little bit once we're able to evaluate these trigonometric functions. So be sure to take these derivatives carefully. We're going to test some memory and skills in Calc 1, and eventually some Calc 2 skills will show up here and there. Nothing too heavy, but don't forget when we take this function, the derivative of these functions, there's a chain rule for each of those components. Sine squared is 2 sine of t times cosine of t. Cosine of t being the derivative of sine, and sine being the inner function in this chain rule situation. Similarly, we get negative 2 cosine t. That's the derivative of cosine squared, or the square of cosine. And, well, 2 cosine t is the derivative of cosine squared, times negative 2 sine of t. That's the derivative of cosine itself. So outer is the squaring function, inner is cosine t. Derivative of cosine is negative. That's why the minus sign is there. Now, lastly for tangent, it'll be 2 tangent of t times the derivative of tangent, and the derivative of tangent is secant squared. So we have what remains there, 2 tangent t secant squared of t. Now that we have the derivative, we're going to need the magnitude of this derivative vector. It's quite a bit of mess, but remember that we just square each of the components and add them up, put them all under a radical, or take the square root of all of them, or to the 1/2 power. That takes care of it just as well. In the next line, we factor out a 2 because everything has a common factor of 4. So we factor out the square root of 4, and that's what gives us this 2. Now what remains inside should make sense as a factored out portion of things. We've added up 2 items that were essentially the same, right, to get this value here. Once we factored a 4 out, there was sine squared, cosine squared, and then cosine squared, sine squared. 2 of those gives us that coefficient. So that's our magnitude. So our unit normal vector, or sorry, our unit tangent vector, t of t, would really be this long expression with a bunch of t's in it. So it would be a function, only we're asked to find it at the specific value t equals pi over 4. So what we've done in this line is we've put together our formula for the first time in the problem, and we've substituted t equals pi over 4 for all our t values. We begin our evaluation. It's a little tedious, there's a bit of work to it, be careful, but there shouldn't be anything too difficult in it all. Once we evaluate, we arrive at this expression right here. I've left that sort of strange looking 1 over root 5, or 1 over the square root of 5 over 2 out as a scalar multiple of the vector, just to simplify writing it down. It's fine either way to multiply that in or to leave it out as a scalar product. Again, just be sure that you understand what an answer prompt might be asking for in WebAssign or a quiz or test or something. On a quiz or test, this is likely to be just fine, as we have it written below. So that's the unit tangent vector. Sometimes you'll find it at a point. Sometimes you just leave it as a bunch of t variables in the expression. Okay, so the definite integral of a vector function. This is just going back to doing calculus in 3 dimensions. And really, all it is splitting up this evaluation of this definite integral along the 3 components and integrating just as you normally would in a single variable. And you just do that 3 times. So let's see what we have below. So in the below example, we're asked to evaluate the definite integral here. And what we'll end up with is just splitting that integral over each of the components. There's a j component and a k component, which have actually been overlooked here in the answer. So I need to add a j hat here and a k hat so we don't forget it. Again, j hat and a k hat, j hat, k hat. Okay, so that keeps us in a vector form. So notice that answer was actually a scalar, and that would have been incorrect to leave it that way. What happened was that I just forgot to write the notation as I went along. So again, though, there's nothing really special about this other than remembering a couple, older integrals. We can use trig substitution to integrate this first integral, or you can just remember that the antiderivative of 1 over 1 plus t squared is arctangent of t. The other way to do that is to recall that, so I think that's both ways. Trig substitution or just recalling what the derivative of arctangent of t is too. That's another nice way to get there. For this one, it's a u substitution. Notice that 1 plus t squared has derivative 2t. So 2t dt becomes our du. U is down here, and through our u substitution, we're able to evaluate that as natural log of 1 plus t squared. Here's that for arctangent of t. We evaluate it at our limits of integration to arrive at the constants we get below, and our ultimate expression is this. In vector form, it might not hurt to write that down just to remind us that this actually should be a vector. We can finish this problem off a little further. There's no x component, so that's just a 0 there. It's 0 I, essentially, pi and natural log 2. So when we evaluate, or when we have the integral of a vector, our result is a vector, just like the derivative of a vector. And just like the unit tangent vector of a vector function. Okay, so lastly at the bottom, find the solution to the differential equation with given initial condition. So it's a very simple differential equation. If we're given a derivative and it's equal to some function, a solution to a differential equation is finding the function r of t, right? That's what we're asked to come up with. What is r of t if its derivative is as such and it has this initial condition? The function satisfies this initial condition. So in order to get rid of a derivative to find r of t, all we need to do is integrate. So r of t then is equal to this integral. We just integrate all 3 components of it. Be careful with that. This should be a u substitution. U equals 16, u equals 3t, and this one doesn't need much. It'll be 5/2 t squared. We see that in the next line. And once we've integrated each component, we've got this line here. Remember that the antiderivative of sine is negative cosine, so to be careful with that. The u substitution, if we used it, we'll put in a negative 1/6, or we could have just sort of mentally worked our way through that. Either way is fine. The most important part of this line is this is the indefinite integral so far. So we have constants of integration for each one of these. Okay? You might see this written sometimes as the vector c, and we'll write that as its components c1, c2, and c3. Then we could have added up the vector of antiderivatives without constants plus the vector c. We wrote it all split into component form with the c's in each component, and that's just fine. So the last thing we can do is determine those c values. We've done this sort of thing in a Calc 1 class. And to determine the c1 values, all we need to do is plug in or on one side of the equation, set this vector 6, 5, 2 equal to r of 0. That is, in fact, our initial condition. And then what does that mean in terms of our given function r of t that we found? Well, it's this. We evaluated t equals 0 to come up with the values that we have listed along here. So it looks like once we solve for each of our c values, we get these values of c1 through c3. We plug those back into our r of t equation to arrive at what we have at the very bottom of the page, our final answer for this. And that's as follows. Okay, so again, it's not different at all from what we did in single dimensional calculus. It's just doing it 3 times, once for each component, each space. Leaving this in vector notation makes it really feel very familiar. So in other words, using the angle bracket notation makes it feel very familiar to a Calc 1 class. Only you're doing each of this, you're doing 3 problems in one, in some sense. Be careful if you do use the IJK notation, because you could lose track of them like I did in that example. So don't do that. Okay, so that should conclude 10.7. Have a look at the examples in the book, and good luck with these problems.